Hey there, folks. Good morning. Happy Monday. Today's problem introduces the Crab Nebula, which is a massive collection of glowing gas that's found about 6,500 light years away from Earth. In case you're unfamiliar, here's a pretty famous picture of it that was obtained by the Hubble telescope back in 2005. It's very pretty. However, there's a very powerful and mysterious energy source that's buried deep within there. The problem description tells us that energy is released by this nebula at this exceptionally large rate, a rate which is roughly 100,000 times that of the sun. That's a lot of energy. Where is it all coming from? Well, it appears to be stemming from a rapidly spinning leftover stellar core known as a neutron star. Down below, we're provided with the neutron star's rotational period as well as its change in rotational period per second. So this implies that the rotation of this object is actually slowing down over time, since we're adding this tiny quantity of time to the period for each second that passes. Let's try and learn more about this object using some of our rotational concepts that we've covered in this chapter. In part A, we're going to find the neutron star's moment of inertia. And then in part B, we'll use that result to calculate its radius in kilometers to get a sense of its size. Next, in part C, we're going to determine the linear speed on the surface of its equator. And the speed of light will be our benchmark to compare it to, since this thing is just spinning so fast. And finally, in part D, we're going to justify the statement found at the bottom, which claims that a neutron star is essentially a large atomic nucleus. How are we going to do that? Well, we'll calculate its density and then compare it to the density of two different objects, one of them being just ordinary rock and the other being the density of actual atomic nuclei. So there's a lot of parts to do here. Let's go ahead and get started and kick it off with part A. The first thing we should do is grab the equation for the rotational kinetic energy of an object. We're not provided with the angular speed omega, but we do know that omega is equal to 2 pi divided by the period. And we have the period. So let's go ahead and substitute that in and square it. Take a moment to reduce the expression down at the bottom to the following. And now, what are we supposed to do with it? Remember that we were told how much energy is radiated by the nebula. And that energy is coming from the energy that's lost by the neutron star every second. So this means we can take a time derivative of this expression, and once we figure out the result, we can set it equal to the amount of energy that was mentioned in the problem description from earlier. And we should be able to use all of that information to solve for the moment of inertia of the neutron star, which is capital I. First, let's factor out all the other constants from inside the parentheses here that don't change over time. So that'll leave us with a derivative of 1 over the period squared with respect to time. Now, we've seen this kind of situation in a couple of the videos already, where we can use the strategy of changing the exponent from a positive value in the denominator to a negative one in the numerator. And then we can just really easily use the power rule. So that's exactly what we're going to do here, starting with what you see in the next line. The constants out front can be left alone for the time being. We're going to bring them back into the picture once we figure out the derivative. So for now, we're just going to deal with this piece specifically. And to make matters worse here, since we're taking a derivative of a variable that's different from the differentiation variable, we need to also utilize the chain rule. And I want to give a quick reminder on that in case you're not familiar or maybe not comfortable with using the chain rule in these types of situations. First, you really want to just identify the inner and outer functions of this expression that we're trying to take a derivative of. Let me go ahead and grab a pen here to make this a little more clear. What's our outer function in this quantity? Well, it's going to be the function that raises the variable itself to the power of -2. Okay, so that's kind of like our outer function. Okay, so what about the inner one? Well, the inner function is just the variable itself, right? It's just the period. So now we've identified the inner and the outer functions, which will make setting up the chain rule a little easier. So let's move on to that next. Here you can see that I've set our substitution variable in the chain rule equal to the innermost function. And when we take a derivative of both sides of this equality, it says that the derivative of our substitution variable with respect to time is equal to the derivative of the period with respect to time. And we're going to use these two parts in the following way. Let me go ahead and switch back to a regular pointer arrow like this. There we go. So our chain rule says that the derivative of the period to the -2 power with respect to time is equal to the product of two other derivatives. The first derivative on the right requires us to replace our inner function with our substitution from above. And now we're going to take a derivative of the outer function with u as the inner one with respect to u. And then multiply that by du dt, which we actually have already. That's up here, right? We know du dt is d capital T dt. So this whole thing can look a little intimidating, but really we only have one piece we need to worry about, and that's this one right here. And this section is where the power rule comes in. So the -2 in the exponent on u is going to become our new coefficient. And then we're going to subtract 1 from -2, which will give us -3. Okay, so we're going to have -2 times u to the -3 power multiplied by d capital T dt, just like this. So that's really all that we have to do for our derivative. There's just a few remaining steps in order to make it usable. The first step is to put u back into the denominator so we can flip the exponent from being negative to positive, like this. Next, we're going to replace u with our original variable, okay, which was t, kind of like how we defined up here in the top line. So when we put that back, here's what we get. And then finally, let's not forget about those constants that we factored out from before. We'll bring them into the picture, multiply them by what we have here, and then take a moment to simplify and reduce. And now we have our derivative. This is what we wanted. So let's move on to the next part. I said before that we were going to set that derivative equal to the energy that's lost by the neutron star. And since the energy is being lost, we can represent that mathematically by putting a negative sign on this energy term on the left-hand side. And since we know the derivative, let's go ahead and plug that in next and check this out. We have a negative sign on the left, negative sign on the right. They both cancel out. And now we can solve for a moment of inertia that's positive, right? It needs to be positive, so this works out really nicely. If we multiply both sides by the cube of the period, and then divide both sides by 4 pi squared times the change in the period, well, now we get the moment of inertia isolated on the right. So we're ready to plug in some numbers and see what we get. However, one quick word of warning. We need to change these watts units to joules per second. Thankfully, it's a really small change. All the numbers will remain the same. There's no weird conversion factors involved there. We're doing this so that we keep the units in a proper format as we go along, and our moment of inertia result is in kilograms times meters squared, right? We don't want watts in there. So when we take this second line here and put it into a calculator, we end up with the following. Approximately 1.09 times 10 to the 38th kilogram meters squared. And that's our answer for part A. And with that done, we can now move on to part B and get the neutron star's radius. Since we want to model this object as a solid sphere, we're going to need the expression for the moment of inertia for that kind of geometrical shape. So here's our starting point. The goal here is to use this expression and solve for r. So that's pretty easy, right? You just divide both sides by 2/5, as well as the mass, and then take the square root of both sides. Okay, pretty easy. Now we can start plugging in some numbers. Here in the numerator, for the moment of inertia of this solid sphere, I've plugged in our result from part A. And in the denominator, we're using 1.4 times the mass of the sun. And now we're ready for the calculator. Entering all this in, I get the following. But we're kind of in trouble here. The result is in meters. We need to adjust that to be kilometers. So what we can do is take this result and multiply it by 1 kilometer per 1,000 meters. And let's also report it to a relatively small number of significant figures, just to be safe. Let's say 2 of them. What do we get? Well, it looks like just under 10 kilometers. So isn't that crazy? Something with a radius out in space that's maybe around 10% larger than the height of Mount Everest is spinning so fast that it's putting out approximately 100,000 times the amount of energy that the sun does every second. That is absolutely wild. Crazy. Speaking of spinning, we need to calculate the linear speed next for part C. Remember that the linear speed for rotating objects is found using this expression, and we can use the same substitution of 2 pi over the period to plug in for omega, just like we did in part A. So let's go ahead and do that next. Let's see, we have the radius, we have the period, and so this part here is really just plug and chug. One extra thing I'm going to include in this product is a conversion factor at the end, which will give us the linear speed in terms of the speed of light, which is this value here in kilometers per second. So with that included, we find that A point on the equator of this neutron star has a linear speed of about 6.3 thousandths of the speed of light. And that's the answer to part C. Now, that doesn't seem very big, since we're using the speed of light as a benchmark here, but that's like 4.25 million miles an hour. So don't be deceived by this value. It's pretty fast, especially for something that small. Anyways, on to part D next. We're going to use this equation here to get the density of the neutron star by plugging in the mass for m, and then in the denominator we will use the volume of a sphere. So, a pretty simple approach here. Do be aware that since we're comparing this density result against other densities that are in kilograms per cubic meter, our result here should have the same units as those as well. And that's a pretty easy thing to incorporate. It's just down here in the denominator, when you're doing 4/3 pi r cubed, include a conversion factor for r that switches things over from kilometers back to meters. And so putting this into the calculator, what do we get? Well, it's about 6.9 times 10 to the 17 kilograms per cubic meter. And that's our answer. That is definitely higher than the density of rock. And it's, in the same order of magnitude as the density of an atomic nucleus. So it looks like the statement about neutron stars essentially being giant atomic nuclei is accurate, at least using the numbers that were provided for us in this problem. And now, we've covered a fair bit in all these parts, and I think it might be best if we do a quick recap on the solution card to review. So in part A, we used the equation for the rotational kinetic energy of an object, and then we took a derivative of it. And when we set that derivative equal to the amount of energy that was lost by the neutron star, we were able to solve for its moment of inertia, which is this value here. In part B, we used this moment of inertia value in conjunction with the equation for the moment of inertia of a solid sphere, allowing us to solve for this radius in kilometers. And then part C and D both used this radius result, but for different things. Part C used it to get the linear speed of a point on the neutron star's equator in terms of the speed of light. And part D used this radius value to calculate the neutron star's density. And that is everything that we needed to do here. The problem is done. I hope you enjoyed this one as much as I did. Neutron stars are certainly an interesting thing to evaluate, and I'm sure that we will encounter more about them in the future. So stay tuned. Thanks for watching, guys. Have a good one.